A major bank moves a core wire transfer system from an IBM mainframe to Java microservices using a popular AI coding assistant. The Java compiles. The unit tests pass. The first transaction in UAT crashes the database. The autopsy finds one variable defined thousands of lines away in a file the model never saw. That bank is not unique. Between 70 and 80% of legacy modernization projects fail to meet their objectives, even before generative AI entered the picture. The wrapper era promised a third way, automated refactoring on demand. It delivered syntactically perfect code that breaks at runtime. The thesis of this paper is simple. Software is not text. Software is a graph, and graphs cannot be translated by stochastic text prediction. Standard wrappers retrieve context with naive REG. They search a vector database for snippets that look textually similar to the query and feed those snippets to a foundation model. Two failure modes follow. First, contextual myopia. A variable named account balance, modified in section and read in section Z 5,000 lines away, never appears in the same retrieved chunk. Second, the lost-in-the-middle effect. Empirical research shows a U-shaped attention curve. Models recall the start of a long prompt. They recall the end. Performance degrades sharply for information located in the middle. When the model overlooks a definition, it does not stop. It hallucinates one. The remedy is the repository-aware knowledge graph, built in 4 phases. Phase 1. Treesitter parses the legacy codebase across 13 languages, including COBOL, JCL, PL/1, and Java. Every file becomes an abstract syntax tree. The parser respects logical boundaries. Code is chunked by section, by paragraph, by method. A function is a discrete unit of logic, not a random span of text. Phase 2. The semantic forge extracts entities and relationships into a graph database. Entities are classes, paragraphs, variables, database tables, API endpoints. Relationships are explicit edges. Calls connects a paragraph to the subroutine it invokes. Updates table connects a logic block to the DB2 table it modifies. Imports copybook connects a source file to its dependency. Defines variable connects a data division to the variables it creates. Phase 3. Symbol resolution. The system recognizes that ACT10UM and file and ACT10UM and file B refer to the same entry in a shared copybook and merges them into a single node. Cross-modal merging links a PDF requirement document describing the user API to the Java class named user API through embedding similarity. Intent meets implementation. Phase 4. Transitive closure. When the system analyzes module A, it does not stop at direct neighbors. It traverses module A to module B to module C to identify the root of truth for every variable. The bank's wrapper saw module A. The graph sees the entire chain. Consider the bank's failure under the new lens. The variable TRN-LIMIT was defined in a copybook, thousands of lines from the execution block, with a REDEFINES clause allowing the same memory address to hold 2 data types. The wrapper saw a numeric field. The graph sees a packed decimal merged with an integer redefinition, flagged at parse time. Data flow analysis goes further. A paragraph reading gross income is identified as having an input dependency. The generated Java method takes BigDecimal gross income as a parameter. Implicit global state becomes explicit parameter passing. Go-to statements, anathema to Java, are flattened. A backward jump becomes a while loop. A skip becomes an if else. A jump to exit becomes a return. Unreachable nodes are flagged as dead code, typically 20 to 30% of a legacy codebase, and removed before migration begins. The compile-fix loop closes the system. Generated Java compiles in a sandbox. If the compiler errors, the agent queries the graph for the missing dependency and regenerates. The human supervises strategy, not syntax. 3 modernization paths exist. Manual rewrite, high cost, high risk, slow. Wrapper AI, medium cost driven by debugging hallucinations, high risk from hidden bugs. Repository graph AI, low cost through automation, low risk through deterministic verification. Productivity differs by a factor of 2 to 3 over standard AI tools. McKinsey data suggests that generative AI can reduce coding tasks by 50%, but only when deployed correctly. The deeper argument is auditability. The graph provides a citation chain for every line of generated code. "Trust me, I am AI," becomes "here is the dependency that justifies this import." In regulated industries, that distinction is the entire difference. Code is not text. We engineer the map. Read the brief on repository-aware knowledge graphs and the four-phase semantic forge that turns legacy modernization from a stochastic gamble into a verifiable engineering process.